Alrighty, so today we want to do two things. We want to remind you about how you can sketch a quadratic, and that should be nice, easy stuff. We also want to give you time to actually start your investigation and to give you an idea of what it is that you have to do. Okay, so go through it together. Does that sound like a plan? In order to do your investigation, it's all about looking at the properties of quartics. So you might just want to make sure that we remind ourselves about quadratics, but it is going to be running a little bit sort of separately. So you'll have to do a little bit of bookwork and then you'll have time to work on your investigation. So those people who didn't download and didn't have a play with the fxdraw, you're going to be having to do that and you're wasting a little bit of your time. Alright, so that's why when I ask you to do stuff for homework, you really need to make sure that you do it. Okay, so we keep going over this over and over again. We've talked about this before, but our properties of a quadratic, if we want to sketch it, we first know when it's going to be concave and convex because of, what's it called? How do we know if it's concave or convex? What's minus or plus? I need proper language now. Right, the A, which is called your leading coefficient. All right, so when we've got it in the form y equals a, x squared plus bx plus c, and a can't equal 0, a is termed our leading coefficient, or you could just say the coefficient of x squared. But you're just getting used to this language, right? And so when a is greater than 0, yes, that's when it's convex. When a is less than 0, that's when it is concave. So that's like so. Okay, to find your x-intercepts, that's when we're solving a quadratic. So that's when you factorize, you quad formula, you use your calculator. You could complete the square, but well. Your y-intercept, that is when x equals 0. That's always a nice, easy one. To find your vertex, right? You completed the square to solve. To find your x-intercepts, you can also complete the square to find your vertex, right? So hopefully you might remember when it's in the form x minus h squared plus k, your vertex is going to be hk. Do we remember that at all? Vaguely flashing a little bit. No, that's all right. Not a drama. So we will remind you about that. And we've also got a formula that if I go x equals minus b over 2a, that gives you the x component of your vertex. Okay? So x component again, I'll save all of this for you, so if you want to, you can get it down later, or you can get it down now, I don't care. How else can you get the x component of your vertex? That is your axis of symmetry, the minus b over 2a. There's another way to get it. I just circled your x-intercepts. How is the x-intercept and the axis of symmetry, aka your x value for your vertex, how are they connected? Yes, Karen? It's the midpoint, right? So you could say it's the midpoint or average of your x-intercepts. Okay, it's not a trick. It's not going to be anything challenging. It is, you know, if you've got two x values there, the middle of it, it has to be where your axis of symmetry is, otherwise it's not symmetrical. Is that reasonable? And if you think that they're jumping around a little bit with all this, yes it is. There's so many bits and pieces with the quads. It does all tie in together. Just be patient. Be patient at the moment. But I'd like to think that so far we are quite happy being able to factorize. We recognize that the vertex is going to be right smack bang in the middle of your x-intercepts. Most of the time, I mean, yes, very nice, but I would tell you most of the time you're going to go, oh, minus b over 2a. All right? We know this. So they're asking you, can we sketch a graph just from an equation? Let's try and do it without using our graphics calculator. I mean, a bit of a shame. They've shown you that already. But just from looking, it's a 2 and it's a positive 2. So we know that it is convex. Just be careful, because some nasty people could trick you and switch this around. So if I had given you y equals 2, x take 3, 1 take x, would you still say that that is convex? Well, some are nodding yes, and some are just staring, going, I don't know, I don't want to make a decision, and others are going, no. So remember what we said. It's when you've expanded it, right? When it's in the form ax squared plus bx plus c, when that is negative, that's when it's going to be concave. When it's positive, it's going to be convex. So if we have a look at this and we expand, x times 1 is x. What's x times minus x? It's negative x squared, take 3, and then plus 3x. So if I was to now gather my like terms, when I now expand that, yes, I got stuck on 2 times 4, right? You can see very clearly that it is now not actually a positive there. So don't just look at that number out the front, actually then go and look at the rest of the equation. If it's nice, oh yeah, xx, sweet. Okay, so just be careful of that. People don't mean to deliberately trick you with that, but at the same time, you've got to be savvy and up with the flow. So yes, we know that it is concave here. How would you compare y equals 2, x plus 3, x take 1 with just x plus 3, x take 1? What happens if the 2 wasn't there? What would the graph look like if that 2 was not there? They're making signals with their hands. Yes, it would be wider, wouldn't it? Okay, so the 2, remember? The 2 makes it skinnier, flips it, or makes it wider. So the smaller the value of that a, the wider it is. Do we agree? So again, just thinking about some of these things so you know what your graph should look like. All right, minus 3, 1. They haven't actually put it in there, but where would my axis of symmetry go? So what is in between minus 3 and 1? Yeah, and you could just, minus 2? Minus 2 would be more this way. So let's add them together. What's minus 3 plus 1? Minus 2, and then halve it, because there's 2 of them. We're finding the average. So minus 3 plus 1 is minus 2. Does it look like it would be minus 1 going right down the middle? Yeah. Okay, so not rocket science, just nice and simple. If we look at this, we're not surprised that it's going to be concave. Why? Because, yes, x times x is x squared times minus 2. Yeah, it's negative. This is all good, all good. And of course, what would you tell me your axis of symmetry is for this one? What's in between 1 and 2? 1.5. All right? So we're getting over and we're ahead of these guys. We're up with it. Please notice when it's a squared, that's what we call a repeated root. And so it touches. It just touches. Happy? Okay. They're very happy. They're all nodding. So we're going to do quick sketches of this without using our calculator yet. So ruling up, exercise 2D2, first 2, last 2, because we sort of know what the coefficient does. Okay, you need to use a ruler. Your graph does not have to be massive. Probably maybe, I don't know, 3-4 centimetres? 4 centimetres by 4 centimetres? Does not have to be massive. All right. When we're looking at this, we straight away can see, hey, it's going to be convex, okay? This is in your head you're doing this, right? You know that it's going to look like this. Maybe if you want to, you could write down that your x-intercepts are going to be 4 and -2. Sorry, do I have to write bigger there? Bigger, write bigger. Do I have to write bigger? Okay. So 4 and -2, it's going to be convex, and just because you're so wonderful, what's your y-intercept? I haven't heard anything. Hello? -8. So remember, your y-intercept occurs when x is 0. So that's not there, that's not there. What's -4 times 2? -8. So you can just look and you've got that, just that little bit of extra information. So here we go. You get your ruler. You don't even have to do this to scale because it's a sketch. But obviously you want it to be, you know, okay. And I'm going to go over here. That's -2. This is 4. Big tip. Draw your graph first, right, through your x-intercepts. Then put your y-intercept in. If you go dot, 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 and you try and connect all of them, you get funky looking graphs, right? Remember, it doesn't have to be to scale. We polish it off. That's my y-axis. That's my x-axis. You probably don't need to do anything more because they're not asking, but I just can't help myself. I can't help myself. Because I reckon I know what my axis of symmetry is. What is in between -2 and 4? -2 plus 4 is 2. And what's 2 divided by 2? So I'm an overachiever. We pop that in. And it looks impressive. Right? Make sure. Label your axes. Label your x-intercept, y-intercept. That's just an added bonus. So first off, is it concave or convex? Convex, love it, love the language, and we know that it's going to be touching at what point? Touching, because of that, right? And x equals -3, because it's a perfect square. So we will go like so. I'm going to now just go, here's my -3. Try and keep it symmetrical. It's very hard. I'm at the side a little bit, not too bad. So this is a sketch. I don't know how far, but now I can add what this is. So remember, what did we say? This is my y-intercept. Where do we find our y-intercept? When? When x is equal to 0. So what is 0 plus 3? 3. 3 squared is? 9 2s? 18. Huzzah. If I now had, let's go, give us another number out the front. Let's go y equals 6. Okay, we'll go 6, but I'm actually not going to have, right, the reason I made a funny face and shook up a little bit was because if I now do this, I'm still touching at -3, but what is my y-intercept now? When x equals 0, yeah, 0 plus 3 is 3, 3 squared is 9, 9 6s, 54. There's no way I have enough, there's no way I have enough room for that. So that's going to be, you know, well, here's, let's say here's 54 up here. Ooh, whoa. And what would it look like if it was minus? Well, it's just going the other way. Yeah? Just because that little thing hovers right over the thing, and I can't do it when it's on pause. So, sorry, just fast forward this. You'll see my method to my madness. And I'm looking at Cooper because he just did this one where he said he decided to start with A and went through and go, okay, what's it? You want to talk us through it? Wait. You can have that. Here you go.
We looked at the x-intercepts first. You want me to explain all of it? And then we crossed out the one 1 and 4.
Which meant
That we crossed out the ones without 1 and 4.
so it couldn't be that one. It couldn't be that one because it's not 1 and 4.
Yeah, because they're minuses.
Right, so they're not in the game. Right?
Yeah.
Next.
Then we looked at the shape, if it was convex or concave.
Yep. This had to be what?
It had to be convex. So then we had 2 left, and we looked at the x-intercept. No, the y-intercept, which was 8.
How did you get 8?
2 times 4.
Right, so
Right? Yeah.
so that's 0 minus 1, you could say minus 1 times 4
What?
times 2, so it's 8.
I can't keep
It
up.
had to be
Yeah.
that one. So we can go.
Oh. Means it has to be C. It means A is C. Yeah.
No, it's harder behind.
Oh, that one.
Keep going ahead.
No.
No, wrong one.
Right, it's alright. We'll go to plan B. What's the -3? So that one is A. Right, who's coming up to do the next one? So this one was A. Are you okay? Gone. Who would like to come and do B? Come on, play on the board. It's good fun. Come on, Dawkins. Come on. We've got a guest presenter coming to the board.
What? Okay. Oh, that's unlucky, guys. Unfortunate. I don't know. Hi, Amara. B.
Hi, Ellie.
It's a negative, so that means.
Don't leave Ellie out.
Oh, hey. Negative, so that means it will be concave. Yeah. So that one's gone. What's it called? Y-intercept is -4.
No, the x-intercept would be.
The y-intercept's -4.
But haven't you just got a negative out the front?
Oh. So that'd be
And
4.
We're looking at x-intercepts of -1 and 4. So I would say this one's gone. This one's gone.
All right.
Right?
Witchcraft.
This one's gone.
She has no pen. Thought I had the power.
So
okay.
we don't even need.
So Miss Mac took the light off of me, but
I did not
think
take
that's
the I just used the finger.
she's lying. Who's up next? Brody.
Go, you use the finger. Go and use the finger.
What are you?
And you have to actually label. Yeah, but you have to label, so this one's B.
Okay.
Okay?
Okay.
Now, anyway,
Yeah, you have to
I think
analyse.
everyone's got the gist now. I think we've got the gist. You can finish it yourself, will we?
Doesn't matter.
Presenter number
I don't know how to explain it. I just
3,
know
and I feel quite short. There's your clue.
Hello. So that's flip. That's what? Oh, 1, 4. That's a 1. That's a 4. Oh. I like this board.
That's a highlighter, man.
It's a 1 and 4 because it's flip, and then that's the X,
Yeah, we got it. Nice.
and then the Y is just -1 times -4, which is 4
Yep.
equals
And it's
4.
concave or convex?
It's convex.
Yep.
Convex.
So that leaves us with just, it's that one. Put C in little C. That's the way. Now, Saskia was mocking you, so you're up next now. Pass the pen.
I gotta
Rest
raise
of
it.
us, please, feel free. There's another matchy that comes.
Do I raise this? Do you want to raise this?
No. It's all good.
Saskia.
Sas can do the next one, because we do have to move it on. That is a little bit new to us, but I'd like to think you remember from last year. But if you didn't, that's okay. When we're looking at this, we should see that this has got a vertex of, reverse the sign, keep the sign. So it becomes 1, 3. Is it concave or is it convex? Convex. Excellent. So if I was to sketch A, no calculator in sight, it's convex. I've got, here's 1, here's 3, right? It's going to be nice and, tried to change colour but didn't go. I'm too quick. It's got its axis of symmetry here is x equals 1. So if I told you, expand that and try and solve, what would you say to me? Solve for its x-intercepts. What would happen? I'd get no x-intercepts. What would be the value of the discriminant? Oh, what was the discriminant? I see the looks in your eyes. Who can remind us what was the discriminant? It's the triangle. It's the thing. Yeah, it's the thing underneath the square root, right? So we would know straight away, because there are no x-intercepts here, this means your discriminant is less than 0, because you can't square root a negative. If you were doing your whole solve using the square, so we're solving 0 equals x, take 1 squared plus 3. How do we solve this again? We chuck the 3 on the other side. Stay with me, Dan the man. Stay with me. How do I get rid of the plus 3? Minus 3. And then what would we try and do? Get rid of the squared by? Square root. Can we square root a negative? Negatory, right? So you don't have to do all that, but I'm trying to say, make sure you're realizing this is how it all connects. So when we have no solution, it doesn't mean the graph doesn't exist. It means it's sitting totally above or totally below if it was concave. Okay? It's all starting to whoosh together. All right, what about B? What's that going to look like? What is my vertex for this one, please? It is -2, 1, right? Reverse the sign, because that shifts it. Remember, this is our horizontal translation. It shifts it 2 spots to the left. This is your translation up. Lifts it up by 1. So -2, 1. Let's see, what does that look like now? Is it concave or convex? Concave or convex, peeps? Convex. So cross here. Oh, why is my colour not going? -2, 1. X equals -2. Who can tell me what my y-intercept is? Jazz? Yes, you can. You can get your calculator. No, don't shake your head, because how do you get your y-intercept? You make X equals 0. That is not going to change. No matter what we do to find your y-intercept, it's always going to be x is 0, yeah? Always. So, get our expression here. It's 2. What are we making x? 0. So 0 plus 2 is 2. Squared plus 1. 2 squared is? 4 times 2 is 8 plus 1 is 9. No calculator in sight. Yeah? Do C. I'm grumbling at them because they're not being very nice. So we do the same thing. Match each quadratic with, right? What have you discovered about? Look at A. Is it concave or is it convex? Sask, concave or convex? Concave, because you've got that minus out the front, right? So when I'm looking now, I'm not even, C isn't even in the game, right? No D. I'm just looking at the convex ones. What's the other bit of information I can glean from here? What vertex does it have? -1, 3. Now, let's hope there's only one that's concave and -1, 3, right? If there's 2 that are concave and have the same vertex, what's the decider? The y-intercept. How do you find your y-intercept? Make x equals 0. So, -1, 3. Could it be this one? No. 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 I'm getting a little bit worried. Huzzah! That's the only one. -1, 3. There's no others. So that's got to be A. Done? Right, let's go. Do the next bit. You are going to have a very small amount of time to work on your investigation because you are wasting your class time. I will not feel bad. So if we go to Teams and you go to your notebook, if you want, I can put all of this stuff, I mean the code is already on Daymap. I can pop the investigation there too. I just thought I'd pop it all in one place so you know where it can go. So if you go into your content library, are we there? You go to polynomials. And then we go to investigation. Heading on. Did I save this? God knows. So we've got our actual investigation task. And we'll just have a look-see. I should have opened it already. Okay, so a real polynomial function of degree 4 is a function of this form. So that shouldn't be as any surprise to us. We had the quadratic, that was just x squared plus something x plus a constant. Well, a cubic is when it's something x cubed plus blah, blah, blah. And a quartic is when it is something x to the 4. All happy with that? Excellent. Now, every real polynomial degree 4 can be factorized into one of 7 forms. You're going, what? What are they on about with that? What do we think are these 7 forms? Well, would you agree we can have this form? X minus, as an example, x take 1, x plus 1, x take 2, x plus 2. That's one form. Would you agree? I would say to you that that is different to y equals x take 1 times x take 1 times x plus 1 times x take 2. Why is that one different to the green? Pardon? Aha! This gives you a perfect square, right? So, if we were to now describe this, I would describe this as having 4 distinct real root solutions x-intercepts. Would you agree? Whereas this one, it's got, now this is how you would have to describe it, but we would say it's got 1 real, repeated Yes? And then 2 distinct. Can you come up with another combination that's different to those two? Yes, Hamish? Oof. Absolutely. So what if we had x, and by the way, it could be 1, it could be 2, it could be whatever. I'm just keeping it simple. Absolutely. We could have x take 1 cubed and x, and you know, we've exhausted the 1s and the 2s. Let's be bold. Plus 4. Okay, what would that be? Do you know what we call this? I could say that is a real triple root plus 1 real. Now that's 1, 2, 3. They reckon there's 7 different combos. Can anyone come up with another one? I mean, there's a pattern going on here, yeah?
Y equals x take 1 to the power of 4.
Right, you could have y equals x, and again, it doesn't have to be 1, so let's go plus 2 to the power of 4. So a repeated root 4 times. Yep. Quadruple root. Yep. What about something on this? A play with that. Yep. 2 squared ones, right? So what if we had y equals x plus 2 squared, x take 3 squared? You're getting how you can get all the different combos of these? And each one is going to look a little bit different because we know when it has 4 distinct real roots, that's when it will, or could, cut the axis. Oops. I mean, you guys don't know what a quartic looks like. We're about to do that. But it can cut 1, 2, 3, 4 times. What does it mean when we've got a squared? That's what we were just looking at today. What does it mean when it's got a squared? It is double, but what does it look like? It just touches. Ah! And for some of the ones that, what happens when it doesn't touch? We talked about that with the triangle. No real roots. So what if we had, I'm running out of colours, but what if we had a quad times another quad, right? And this one, its discriminant was no solution. So what happens when it was no solution? What's the value of your discriminant? No, when it's 0, when the discriminant is 0, that's when we've got to repeat it. Less than 0. That's when it won't actually touch or cut. Now, don't get carried away with that. Don't worry. I'm just showing you there's lots of different ways that you can do it. And they said 7. I reckon there's 8 combos that you could play around with. So that's something to consider. To consider. All right. So sorry, we're just giving another demo on fxdraw. So we've clicked on, we open it. This one here, and this is all on the video, and you've got it on this video too. So we click on this that says a little graph, left click, and you think nothing happens, but see here, I can now drag that. I'm holding it down with my left mouse button, and I release the hounds, and I basically get an axis. Now I click, I right click, and I get this. And I can just type in my equation. So I'm just going to go y equals, let's go, oops, shift x take 1, bracket, x take 2, bracket, what do you want to go? Let's go x plus 3, and we'll finish off with x plus 1. Now, why am I doing such small numbers? Yeah, because if you have, 5, 7, think about what your y-intercept is going to be. Because remember, your y-intercept comes by timesing all of these together. That becomes quite big. So I'm just keeping it small. Anyway, I say OK. And you can see that it pops up nice and simple. it has scales just like your whatchamacallit, calculator. So again, if I right click, I can see my axes here, my scales. So you could see my y, if I go here, my y needed to be a little bit lower. So it was -10. I'm going to go a little bit lower. Unfortunately, I haven't found auto zoom on here. So some people in the past have actually used it, typed it into their calculator, gone auto zoom, and then they've adjusted, copied the scale into their doodad here. And of course, if you prefer to use Desmos, by all means use Desmos. Here's one of the joys of FX. You hover it and you can see, bang, the local minimum pops up. Right click, add annotation. Right, we don't care about the number here, so I right click and I can just go, do you know what, I'm just going to call that a TP. What does TP stand for? Turning point. And all you have to do for this investigation is count how many turning points there are. Is that difficult? 1 turning point? 2 turning points? 3 turning points. The other thing that they're going to ask you to investigate is, if we look back here, so we've got turning points, the number of inflection points. What is a point of inflection? That's right. So here it's convex, then it becomes concave. So somewhere along here it is changed from being one shape to the other. That is what we call a point of inflection, right? Notice I'm hovering, and nothing is coming up. You have to actually click in it. Right click. Yep, cancel. Right, see how the green dots? Now, when I hover, things appear. If I sort of go, where do you reckon it's changing from concave to convex? Sometimes it works, sometimes it doesn't. Oh, it's not going to work for me on this one. It actually will sometimes come up. Again, you don't need to actually, I might need to make it bigger. You don't need to tell me what the point of inflection is. You just have to say how many there are. So how many for this graph? 2. I just want to get, that's when, oh, there it is. Oh, there it is. Right, add. And so you could just go point of inflection 1. Yeah? So 1, 2. So does that seem like it's very tricky? You graph a couple. What's up? Tom, what? I don't care what this is, right? All you want to know is how many there are. And you might be going, why do I even need this? I can see clearly. It's convex, then it becomes concave. Well, as you change them around a bit, sometimes it might be a bit squishy, and it might be you can't see it clearly. So that's why you might need a little bit more maths, and that's why you should definitely watch the video towards the end where you can use your graphics calculator to definitely double check. So this is the joy. I can now go like that and it just plops in and I've got it saved. If I want to change this, I can just right click and I can change it. So that's the benefit of having fxdraw. Oops, and I'm just going to get rid of that. They suggest this. This is from the SACE website, okay? You have to write down your function. You have to write how many roots there were, roots, x-intercepts, whatever, how many turning points you saw, how many points of inflection, and I want to see the graph, and it's got to be labeled. What we're saying is don't do all, at least 3. You don't have to show everything there. You can stick the other 2 graphs into the appendix. So this is one that someone prepared earlier. So they have an introduction, right? But this is the guts. They have an equation. They write down what the roots are, that there's 4. How many turning points? I find this is a little bit small. I would probably have that graph somewhere underneath. So it's clearly labeled and I can read it and I don't have to go, what the? The others could be just as an attachment at the end of it. It's called the appendix because you've only got 8 pages for this. Yeah, Tom? I'm just showing you with this. So the A grade depends on what ones you investigate, what you write for the introduction. And I'll just get out of that because people who are now on the video can take a snapshot of that. What I'm going to ask you to do, you can start now, see if you want to fiddle. If you think, nah, fxdraw is not for me and I'm just going to use Desmos, do it. Right? There was a little bit of a rundown on the video about Desmos as well. I think if you log into Desmos, you can keep your graphs. Some students had problems. It would disappear and they'd have to screenshot, and then when they had to go back and change their graphs, it was gone. Some people had that issue with fxdraw. Is look, just do what you need to. However, hello? So I think we've given the game away that when you have 4 distinct real roots, you get 4 roots, you have 3 turning points, and you have 2 points of inflection. That's all you have to talk about, right? That, when you said, I've noticed this pattern, that is what a conjecture is. Don't get worried by that word. It is just, oh look, I looked at these 3 graphs, they all had this in common with they all had the same number of turning points, they all had the points of inflection. So I'm making a prediction to say, do you know what? Every degree 4 that has 4 distinct real roots, they will always have this number of turning points and this number of points of inflection. That's it. Right? Make up another polynomial, so now you've got 4 graphs, and show that it fits that. I don't think that is difficult at all. Would you? That's not it. There's then a part B. So notice, what are they now looking at? What happens when there's a squared? Will you still have 3 turning points and 2 points of inflection? Maybe you will. Maybe you won't. How will you check? Graph it. Have a look. It'll be obvious. Trust me. Write it up, do a table, etc., etc. Okay? So please, I think A and B you could whip out really quickly. We'll carry on next lesson, but I only see you Thursday, Friday. So, homework. I really need you now to be working on this. I would love to have done the next bit in the textbook with the completing the square. Some of you have done it. Some of you was taking a little bit longer and might not remember it. So, investigation, part A, part B. We go.